Hey everyone, and welcome back to the channel. Today we're embarking on an epic journey, not across continents, but across worlds. We're heading to Mars, our enigmatic red neighbor, to uncover a story written not in books, but in the very rocks and dust of the planet itself. It's a tale of a world that was once vastly different from the cold, dry desert we see today. We're going to decode the ancient geologic history of water on Mars. For decades, we've looked up at Mars and wondered, could it have ever harbored life? This question is one of the biggest drivers of space exploration, and the key to answering it lies in one simple yet profound substance: water. Here on Earth, wherever we find water, we find life. So, finding evidence of past water on Mars is like finding a treasure map, with X marking the spot where life might have once thrived. When our first rovers and orbiters sent back images of Mars, they revealed a landscape that was tantalizingly familiar. We saw features that looked just like riverbeds, deltas, and even vast ocean shorelines on Earth. But were they real, or just tricks of light and shadow? Scientists needed more than just pictures. They needed solid geological proof. And that's exactly what we found. The story began to unfold with the discovery of specific minerals. Rovers like Opportunity and Spirit, and later Curiosity, were like robotic geologists on the Martian surface. They drilled into rocks and analyzed their composition, and what they found was astonishing. They discovered minerals like hematite and gypsum. Now that might not sound exciting, but here's the thing. On Earth, these minerals almost always form in the presence of water. Think of the hematite found by the Opportunity rover. They appeared as small, spherical pebbles nicknamed blueberries. These concretions were compelling evidence that groundwater had once percolated through the Martian rocks, leaving these mineral deposits behind, much like how minerals build up inside old water pipes. It was a smoking gun. This wasn't just a theory anymore. We had physical proof that liquid water was once a real part of the Martian environment. But the story gets even bigger. From high above, orbiters like the Mars Reconnaissance Orbiter used powerful cameras and spectrometers to map the surface in incredible detail. They revealed sprawling, fan-shaped deposits of sediment at the mouths of craters. These are ancient river deltas, almost identical in structure to deltas like the Mississippi River Delta here on Earth. You can literally trace the paths of ancient rivers that flowed for millions of years, carrying sand and mud and depositing them into vast crater lakes. One of the most famous examples is Jezero Crater, the landing site of the Perseverance rover. Scientists didn't choose this spot by accident. Orbital data showed it was a prime location, a crater that was once a deep, tranquil lake fed by a flowing river. Perseverance is there right now, collecting rock samples from this ancient lakebed. These samples are the holy grail of Mars exploration. Why? Because if life ever existed in that lake, its fossilized remains might be preserved in the very mudstones that the rover is drilling into. It's a mission to find ancient Martian biosignatures. So we have evidence of groundwater and flowing rivers. What about oceans? This is where the debate gets really exciting. Some scientists believe that billions of years ago, a massive ocean covered the entire northern hemisphere of Mars. The evidence for this is a bit more subtle. It comes from mapping the topography of the northern plains, which are much lower and smoother than the cratered southern highlands. Scientists have identified what look like ancient coastlines, faint lines tracing the edge of this hypothetical Oceanus Borealis. Imagine it. A young Mars with a thicker atmosphere, blue skies, fluffy white clouds, and a vast northern ocean glistening under a fainter, younger sun. Rivers would have flowed from the southern highlands, carving canyons and valleys, and emptying into this great sea. It's a breathtaking vision of a world teeming with potential. So what happened? Where did all the water go? This is the tragic second act of Mars's story. Unlike Earth, Mars is a small planet. It has less gravity, and crucially, it lost its global magnetic field early in its history. Earth's magnetic field acts like a shield, protecting our atmosphere from being stripped away by the solar wind, a constant stream of charged particles from the sun. Without this shield, the solar wind began to tear away at the Martian atmosphere, bit by bit, over millions of years. As the atmosphere thinned, the air pressure dropped. Water on the surface could no longer stay liquid. it began to boil away into space or freeze. The planet grew colder and colder. The rivers dried up, the lakes evaporated, and the great northern ocean either sublimated into the thin air or froze, becoming buried under layers of dust. Today we know that a significant amount of water is still on Mars, but it's locked away. It's frozen in the polar ice caps, which are a mixture of water ice and frozen carbon dioxide. There's also a huge amount of water ice buried just beneath the surface, especially at the mid-latitudes. Radar instruments on orbiters have detected what appear to be massive, glacier-like deposits of subsurface ice. Some of this water may even exist as super-salty brines that can stay liquid at very low temperatures, which could potentially be a habitat for extremophile life even today. Understanding this history is not just an academic exercise. It's fundamentally tied to our search for life beyond Earth. If Mars had liquid water on its surface for hundreds of millions, or even a billion years, that's a significant window of time for life to potentially emerge. The journey from a watery world to a frozen desert tells us about the fragility of planetary habitability. It serves as a cautionary tale, showing how quickly a world can change, and it also provides a roadmap for future human exploration. Knowing where the water ice is buried is crucial for planning future missions. Future astronauts on Mars won't be able to bring all the water they need with them. They will need to live off the land, a practice we call In-Situ resource utilization. They will have to mine this Martian ice, melt it for drinking, grow crops, and even split the water molecules into hydrogen and oxygen to create breathable air and rocket fuel for the journey home. The water that once carved canyons could one day sustain the first human colony on another planet. The story of Mars's water is a captivating detective story, pieced together one mineral, one rock, and one orbital image at a time. It transformed our view of the red planet from a dead, static world to a dynamic one with a dramatic and watery past. And the search continues. With every rover that drives, every drill that turns, and every sample that's analyzed, we get closer to answering that ultimate question. Were we alone? Or is there another chapter in the story of life, written in the ancient riverbeds of Mars? Thanks so much for joining me on this journey to the red planet. If you found this fascinating, make sure to hit that like button and subscribe for more deep dives into the mysteries of our universe. Let me know in the comments what you think. Could life have started on Mars? Until next time, keep looking up.